Hello again, this is part 3 in a series of videos where I explain how I developed a Excel spreadsheet that allows the user to model what 100% renewable energy supply would look like for countries such as the USA and Germany. If you have not already done so, you should watch parts 1 and 2, otherwise this will not make much sense. The links to part 1 and 2 can be found in the description below this video. Now, in previous videos I explained how we could input different values of onshore wind capacity, PV capacity, slow and fast charging storage in these cells here to add renewable energy supply to a grid, how we could include the electrification of things that natural gas are currently being used for, the natural gas energy supply in commercial, residential and industrial uses such as heating, and for the electrification of road transport, replacing all fossil fuel vehicles with electric vehicles. In this video, the last video in this series, we're going to explain how the spreadsheet works. So to do that, or how the formulas work to produce the outputs that we saw in parts 1 and 2. So it starts off, the maths in this is very easy, it's just basic arithmetic, addition, subtraction, multiplication and division. Starts off by calculating power based on the capacity factors of the different energy types. So onshore wind capacity factor at midnight at that time was 39.935%. So I'm simply multiplying that by the capacity term up here, 2,300 gigawatts. I'm assuming that the distribution of future wind farms will be similar to the current wind farms. There'll just be more of them. So they'll have a similar capacity factor as the historical value back in 2021. And 2022, 2023, as we had it hour by hour throughout the year. How these capacity factors change hour by hour. So it produces power, the total power produced by the 2,300 gigawatts of wind turbines, all acting with an average of 39.935% of maximum capacity. Then the same calculation in this column for solar. So just multiply the capacity factor found in this column by the capacity over here. Gives us the power generated from solar. For nuclear, took the real generation values, the historical generation values as obtained from that US Energy Information Administration website, the 95 etc. gigawatts of generation. Again, if you want to change the amount of nuclear power, you change this multiplier here. If you want to increase it by 50%, change it to 1.5. And we can see that the power generated from nuclear is in this column, simply changes as you change this multiplier. Set it back to 1. The real amount that was being generated at that time. Okay, so this gives us, so to get the total power from our renewable and nuclear sources, from our wind and PV and nuclear sources, we simply add these values together. From these 4 cells, there's no offshore wind here, so that will always be 0 in this version of the spreadsheet. Onshore wind plus PV plus the nuclear gives us the total power being generated. We compare that with demand. Now the demand, the historical demand that we obtained from the same the US Energy Information Administration website, we had back here the actual demand values. So that's just that value. We added the demand from the needed to recharge the electric trucks and buses, the heavy electric vehicles, because we said they're always being recharged as often as possible whenever they're parked, because they're work vehicles. They run through a lot of their battery each day, so they need to be recharged. We can't choose when to recharge them. We have to recharge them when we have the opportunity. Sorry, at every opportunity. This column is the electrification of the gas supply. So if we're replacing all of that commercial, residential and industrial gas use that we saw, that I described in the previous video, for the US it was this output, for Germany something similar, all of the space heating in winter in the residential and commercial and the industrial use throughout the year. If we're replacing that, we have to calculate how much energy we need to replace it, how much electrical energy we need to substitute for that gas energy. This sum is in 5 parts. I will briefly describe what the 5 parts are. We can see that that there are numbers in here. Just keep your eye on the 94. There's a 94 there, 94 here, 94 here, 94 here, and a 90. There's no 94 there. That's we're using something different. Oh yeah, there's a 94 there as well in the last one. So we see that there's a 94 in each of them. We can see that as we go through hour by hour, that increments by 1, so 94 up to 95, 96, etc., all the way up to 117, I believe, and then it goes back to 94. So that says 20. So the electrical energy needed to substitute for the gas energy, to remove gas energy from use, it's going to be on a 24-hour cycle because we're using it at different amounts during the day. Now, where that is being calculated is down here. So this is the gas calculations in these tables here, putting in the raw gas use, or the gigawatt hours equivalent of the raw gas use, which I showed. Where I got that from, it was from the actual downloaded data in the previous spreadsheet, and multiplying it by these factors here, which I described the use of in the previous video. So putting them in for residential and commercial, the industrial is down here. It's done separately because it's worked out a bit differently. Taking those monthly values, dividing them by the number of days in the month to give daily values over here, so residential and commercial use, the daily use. I've also split it into 2 parts. If you remember back to video 2, I said there's, in summer we can see there's some gas being used for residential and commercial. That's mostly going to be cooking and, say, gas hot water systems. That's going to continue more or less the same throughout the year. The gas hot water might require a bit more energy in winter than in summer. But it's going to be more or less constant throughout the year. So, and then the rest of it, the big increases in winter is due to space heating buildings. So I split that into 2 parts in the calculation. I've kept the cooking and hot water heating here, the smaller amount, and what these values are in this table here is the hourly multiplier. That's the 94 down to 117 terms that we saw in the formulas. So it's basically saying what percentage of the average daily use is being used at this hour of the day. So 3% here for, say, heating hot water in the residential use, increases at meal times, people are using gas stoves, so increases in the morning, a little bit in the middle of the day for gas cooking, and more in the evening for gas cooking. The same thing here for the commercial, increases, say, for restaurants using gas cooking at night, in the evening, lunchtime and morning, and then smaller amounts during the other parts of the day. For the gas heating substitute, so saying replacing all the gas heating with heat pumps. So again, for the residential and commercial, we're saying we're using some of it overnight to keep the places heated at night, with less being used during the day because it's sunny during the day, or hopefully it's warmer during the day than at night, and so there's less need for heating. So again, these are just the percentages being used each hour. You can change these values. I don't know what the actual values are. These are just estimates based on what I've been able to research. If you change them though, the number at the bottom, the sum at the bottom, has to add up to 1 because these are percentages. So the total amount of energy being used each hour, as you add them up during the day, still has to add up to 1. So you get the total amount of energy being used each day, as is given in these columns over here. And then industrial, doing the same thing, convert it to a daily amount, and then split it up hourly, saying the industrial use is going to be less used overnight, but there's still some heavy industries particularly tend to still work at night, so they don't want to turn off their large furnaces overnight, but more being used during the day when most businesses are open. Okay, so that's that 5-term sum for demand for the electrification of the gas supply. So we're adding the electricity used to substitute for that gas use to the current electricity demand, plus the demand used for trucks and buses for electrification of trucks and buses for the EVs, and we're getting a total demand for each hour. We're going to subtract the supply minus the demand, so supply minus demand will give us the difference between supply and demand. When this is a positive number, it means we have more supply than there is demand, and the surplus supply can be used to recharge the storage types, which is the next section of the calculation. If it's a negative number, it means demand is greater than supply and we need to supply more power from somewhere, which we'll get to. First of all, if supply exceeds demand, that value is going to be positive. There's an excess of supply, can be used to recharge storage. It does that by calculating the total capacity that can be absorbed by the storage types, the total power, instantaneous power that can be absorbed by the storage types. So we look at each of the three different storage types, the pumped hydro, the stationary batteries and the EVs that are plugged into the grid. They're in this table here. We're saying the maximum power that the pumped hydro can be recharged at is 20 gigawatts. The maximum power that the stationary batteries can be recharged at is 100 gigawatts. I explained how these values could be changed in part 1 of this video series. They can change them by changing the duration or the capacity of the storage types. The EVs maximum charging capacity is 2010 gigawatts. I explained how that was calculated in part 2 of this series. So we're saying that's the maximum capacity, but sometimes the storages are already near their maximum storage level, and so they can't absorb. For instance, here the stationary batteries are already at 240 gigawatts of their maximum 300 gigawatt hours capacity, so they can only absorb another 60 gigawatt hours, so their maximum hourly power draw at this time is 60 gigawatts, even though in theory they could absorb up to 100. They have 100 gigawatts of inverter capacity, but currently the battery capacity can only absorb 60 gigawatts over the hour. So so the sum here has three terms, one for each storage type, and it says it compares what's the maximum theoretical amount that it can absorb, and then it compares it with the remaining capacity that it can absorb. It says which is the smaller value, choose the smaller value and add it to the sum to get the total power that can be absorbed by the three storage types. So often, very rarely, will the surplus supply be able to supply, say, 2,000 gigawatts here. It can only supply, there's only 191 gigawatts of surplus, so the storage types will not absorb the entire 2,090 gigawatts of their existing capacity, power capacity that they could absorb. So the 191 gigawatts of surplus supply has to be split up between the three of them, and it's split up proportionally based on their current capacity, what they can absorb. So in this case, the pumped hydro could absorb 20 gigawatts, the stationary batteries could absorb 100 gigawatts out of that 2090, and the EVs was 60 gigawatts out of the 90, and the EVs can absorb 2010, so it's 20 plus 60 plus 2010 gives the 2019 total. So these absorb the proportional amount, so 20 divided by 2090 as a fraction multiplied by this will give you the amount of power being absorbed by the pumped hydro. The batteries can absorb, it was 60 divided by 2090 times the 191 gives you the amount of power that the batteries can absorb, and the EVs, it was the 2010 divided by 2090 and then multiplied by the surplus power of 191 to give that the fraction that is being absorbed by the EVs. Again, the recharging isn't 100% efficient, so you have to take into account the efficiency. For the pumped hydro, it was 70% efficient. So the actual change in storage level of the pumped hydro will be this amount times the 0.7 to give the amount that is being added to the 240 existing capacity. Similarly for the for the battery, it's 92% efficient, so you multiply this number by 0.92 and then add it to the existing 240 gigawatt hour level to get the 245 to get the new level. And then for EV capacity, their batteries, so they also had that 92% efficiency, so I'll multiply this number by 0.92 to get the new battery level of the EV capacity. Okay, and we do that hour by hour throughout the year. Now for discharging, when supply does not meet demand, there's a deficit in supply. Some of that deficit in supply can be met by discharging the storage types. Works in a very similar way to charging. It calculates the sum of the three storage types, their total capacity, their total discharge capacity at this time, by comparing their theoretical power limit, how much they can, the maximum amount they can discharge, comparing it with the capacity. So if they have plenty of capacity, this will be the value in the sum. If they're missing capacity, then the sum will be smaller. Okay, but these are conditional levels. You see these formulas are more complicated than the charging formulas. That's because these levels are conditional. They're saying, let's look ahead at our chance of being recharged within the next 24 hours. And we're doing that by taking the sum of the supply minus demand over the next 24 hours. So we're taking the 24 terms in here, the following 24 terms, we're adding them up to find the sum. We're saying if it's positive, it means yes, the storage types will be able to recharge within the next 24 hours. So they're going to be inclined to discharge more capacity. If this term is negative in this column, it means there is a deficit of supply with respect to demand over the next 24 hours based on the forecast of what the weather is doing, how much wind and solar they expect to be generated. And so they're going to be less inclined to discharge their maximum capacity. So they'll discharge less than their maximum allowable amount. And that's what's happening here. We see the maximum allowable discharge would be 1,036 gigawatts, but they're only discharging a relatively small amount, 60 gigawatts in total. Because they're looking ahead and they're saying, well, we're looking ahead and it looks like the weather is such that we won't have a lot of wind and solar power over the next 24 hours. So we don't want to discharge all of our storage. We're going to keep some in reserve for later on. Of course, we know there's going to be more demand later on. We'll get better prices. Or for the discharging EVs, the people don't want to run their batteries flat by sending all the power to the grid. And the software will take care of this. This isn't going to be people making decisions. The individual householders, the owners of the EVs, it's going to be built into the software. They're going to be given an option. At what level of your battery do you want to stop discharging to the grid? They might say 60%. If they're anticipating going on a long road trip over the next couple of days, they might say 100%. I don't want to discharge any energy to the grid. Okay, so this is how the discharge part of the spreadsheet works, discharging from storage to replenish the grid. If there's still existing a deficit, if demand still outstrips supply, then supply is generated from the auxiliary sources. And this column calculates that, so it's just calculating the unmet demand at that time. This is made up from two sources, hydro in this column, existing hydro generation or hydro capacity, and from other generation, which I explained in part 1 of this video, readily dispatchable sources such as biogas, biomass, or anything that can be dispatched as needed. The hydro is determined by looking at historical patterns. Even though there's 80 gigawatts of hydro capacity on the grid in the US, it's much smaller amounts in Germany. They rarely use more than about 56 gigawatts at any particular time. So I just said we'll multiply that 80 by 0.7 when there's plenty of water in the reservoir. This column here keeps track of the water the power that's being supplied by hydro over time. If the reservoir looks like it's going to get low, which I determined using historical amounts, these values are given down here. In this part of the spreadsheet, and these are based on historical patterns. So we go down here, we say this is the maximum amount that can be dispatched, maximum hydro energy that can be dispatched per month for January to April, 30,000 per month. So if this value, the accumulation goes over 30,000, then we reduce the amount of hydro to zero. It's actually stepped down in a couple of steps. Starts at 0.7, then at 0.5, and then down to 0 as the amount of water is being withdrawn from the reservoir. It changes throughout the year based on the existing hydro patterns. I looked them up. Now from the existing hydro generation supply, look at the pattern of use throughout the year. There's more available in the winter, less over summer, and then more available in the autumn again. And no, I did the same for Germany. I did the same for all 3 years for each of the models. So we can get a realistic idea of how the hydro can be used. And then finally, the electrification of the industrial gas supply using the flexible demand, as I explained in the previous video. This is going to be using excess wind and solar. So whenever there's excess wind and solar, that can be used to operate those electrolyzers to provide synthetic hydrogen gas that can be used to substitute for natural gas in the grid. So currently it's all the zero all the way through here, but eventually where it points to where there's excess supply from wind and solar, the storage types are completely recharged, or recharged as they've absorbed as much power as they can absorb, and this excess wind and solar can be used to run the hydrogen electrolyzers up to their maximum capacity, which is in this cell here, the 400 gigawatts. That's why we see a maximum of 400 reached here. And also hydros, some of the unused hydro capacity can be also be used to run those electrolyzers. I'm putting a maximum of 14 here. This also has to look at the multiplier here, because again, if you're using too much hydro capacity, it will decrease because you're running out of water in the dams. So that energy from those sources is being calculated. The electrification amount is being calculated in this cell over here. We just go down here. It's in this cell here above the tables for the gas supply, for the amount of gas. We're saying it's using twice as much energy to create the hydrogen as is being substituted for. So we're basically saying the electrolyzers are 50% efficient. They might be less, you'll have to do research to find that. But that's the starting amount, so that's the total amount of energy we need to supply from the surplus wind and solar and from the hydro to substitute all of that hydrogen gas that's being substituted with the natural gas that's been substituted with synthetic gases such as hydrogen. And it keeps account of that, so as power goes in, this number reduces or decreases, and when the total has been met for the year, it keeps decreasing all the way down to zero, and eventually becomes negative. That means you're generating more hydrogen than you need, and that extra hydrogen can be stored to supply other industries or other uses, or it can be stored for following years' use. Okay, so that's basically how the spreadsheet works. And then the values in the results table here, all these values here and in the graphs are just being calculated in these columns over here. These are just the basically sums of the values over in the left hand side. They're very straightforward. You just look at the formula and they're easy to calculate. Excess wind, excess solar, the values that are appearing in the outputs, the results part of the table and in the graphs. Okay, so that's basically how all of the formulas work. So if you have any questions about how to use the spreadsheet, ask them in the comments section below the respective videos. Again, watch parts 1 and 2. Download the spreadsheet using the links given below and in the description area below the videos. And I hope you find using it to be somewhat illuminating and will give you a better idea of how 100% renewable supply could be applied or implemented on the US and German grids. Thanks for watching.